Assalamualaikum and hi. My name is Nur Azarina binti Azman and today I'll be presenting about our research. The title is Real-Time Computer Algorithm for Trajectory Planning of Robotic Crane. Introductions. The robotic cranes are crucial in modern industries for precise and efficient material handling. However, residual vibrations in crane arms remains a major challenge affecting position accuracy, mechanical integrity, and production efficiency. Rapid movements often introduce jerks, leading to increased vibrations and response time. Effective control mechanisms, such as integrating Arduino with PID controller, are essential for optimizing trajectory planning, minimizing vibrations, and ensuring smooth operations. Despite significant advancements in robotic crane technologies, challenges remain in optimizing trajectory planning to enhance performance, safety, and efficiency. Current systems struggle with effectively integrating feedback control to minimize errors and suppress vibrations during crane movements. Excessive vibrations in the crane arm can lead to mechanical damage, decreased precisions, and longer production cycles. Existing trajectory planning methods often fail to address the complexities of dynamic environments and the needs for precise control over crane movements. This research aims to address these gaps by developing a novel real-time trajectory planning algorithm for robotic crane, incorporating advanced feedback control mechanisms to improve overall system performance, reduce operational risk, and specifically minimize the residual vibrations during the operations. Methodology. So we started by preparing our simulation setup. So we got two simulation setup, which is the first one is robotic crane simulations, and the second one is robotic cranes with pendulum simulation. So both of these simulation we will integrated it with the Arduino Uno and other components such as the motor driver, power supply, the encoder, and also the DC motor. Next is we developing the coding using the Arduino IDE. So basically, there are several components that will be inserted inside the coding, which is the first one is trapezoidal velocity profile (TVP). Second is linear segment with parabolic blend (LSBB), and the third one is for the vibration separation, where we analyze the crane dynamics and will be come up with the equations that will be used in order to satisfy these conditions. Next is we need to find the maximum velocities of the motors. So inside the coding, we need to insert a certain maximum velocity. So in order for us to find the suitable maximum velocity, we will need to generate the RAM input signals and parabolic input signals. The RAM input signal is the linear signals, where the parabolic input is the nonlinear signals, where the RAM input is RT is equal to 80 and the parabolic input is RT is equal to 80 squared. So both of these input signals will be generated using the robotic crane simulations without load. So here are the results for the RAM input data. As you can see from the data, we have the velocity of 10,000, 11,000, and 12,000 count per second. So based on this, we found out that the maximum velocity, the suitable maximum velocity is actually 11,000 count per second. Why? This is because at the input velocity of 12,000 count per second, the system shows significant deviations between the input and output signals. So the gradient is 112.25 and the error becomes substantial. So indicates the control system limitations in handling higher velocity inputs and the necessity for adjustments in the control parameters to improve the performance. So from this, we know that 11,000 is suitable for our maximum velocity, even though they have a slightly errors, but the errors is not bigger compared to the 12,000 count per second. Next is parabolic input data. The parabolic input is instrumental in verifying whether the maximum velocity has been appropriately selected. So when we compare the result of the parabolic input with RAM input, the maximum velocity achieved is equivalent. This is because if you can see, the maximum aggregate speed here is 698 and 682, which is when we compare to the 11,000 count per second that we selected is actually 698, which is not far from each other, so it is equivalent and we can proceed with the maximum velocities of the 698.44 radian per second. Next is we need to integrate two encoders in one algorithm system. So we got like two encoders, which is the encoder one is control the rotation of the DC motor. This one is embedded with the DC motor. The encoder two is measure the rotations of the root pendulum. Next is generate linear segment with parabolic blend from build algorithm. So basically we have like linear segment and also parabolic segment. The linear segment is actually the constant acceleration, and the parabolic segment is actually the acceleration and also the deceleration. So, the simulation result indicates that the area of the system is low and the trajectory is smooth. So, this demonstrates the effectiveness of the LSP method in achieving precise and smooth motions. So, the absence of the loads in the simulation means that the external disturbances or variations in the motor behaviors do not significantly impact the trajectory, which allow for the simplifications of the PID controller by setting Ki and Kd is equal to 0. So by focusing on the professional gains and omitting the integral and derivative gains, a low error, smooth trajectory have been achieved in a no-load simulation environment. Next is we run the simulation using the robotic cranes with pendulum simulations. So this is the pendulum oscillation test data that we collected using the encoder tool. So these excessive vibrations during and after the motion highlights the needs for improved vibrations damping or control strategies to ensure smoother and more stable operations of the robotic cranes. So this is the pendulum oscillation test data. This is actually the data that we gain from the encoder, and also this one is the equation that we get from the vibration separations calculations earlier from the dynamics of the cranes, and the equations need to be satisfied. Thus, in our case, T1 is equal to 0.701 seconds. This is the theoretical graph. During the first motions of the pendulum was supposed to left behind due to the accelerations of the motor. During the constant accelerations, the pendulum will gradually moving forward as the motion is in constant velocity and no acceleration happened during that time. Lastly, the pendulum should return to the initial positions as the motion is slowing down as the acceleration is decreasing and velocity is linearly decreasing. This is theoretical graph that we need to gain. So, the final simulation data, the result that we gained after without using proposed method, even the motor ceases its movement, it continues to oscillate due to the residual vibrations induced by the angular motions. So these excessive vibrations during and after the motions highlights the need for improved vibrations damping or control strategies to ensure smoother and more stable operations of the robotic crane. This is the when we use the proposed method. So based on the results show, the amplitude of the vibration is lower in T1 is equal to 701 than the amplitude of the vibrations in T1 is equal to 700. So comparative analysis. The tests conducted with the proposed methods demonstrate improved stability and reduced residual vibrations, validating the effectiveness of the theoretical approach. It proved that the proposed method where T1 is equal to 2 pi n over omega really reduced the vibrations of the systems. Conclusion and future works. This research successfully developed a real-time trajectory planning algorithm for a robotic crane using an Arduino microcontroller with a PID controller. The proposed approach effectively reduced residual vibrations, enhancing the crane stability, precision, and operational efficiency. Theoretical and practical investigations validated the methods, demonstrating improved motion control and reduced mechanical wear. Key contributions include optimized trajectory planning, effective vibration suppressions, and real-world validations of the proposed control strategy, establishing a foundations for future advancement in core robotic crane automations. Future work will focus on enhancing control strategies through adaptive PID tuning, feed-forward control, and AI based controllers, exploring advanced trajectory planning methods such as time optimal control, S curve motion profiles, and modal predictive control (MPC). Additionally, efforts will be directed towards improving real-world adaptability by testing across various crane configurations and industrial robots, as well as mitigating external disturbances like wind forces and load variations through adaptive control approaches. That's all from me. Thank you.